Okay, so let's take a look at a slightly richer example of an auction. And in particular, we'll stick with the first price auction. And again, now let's think of, instead of just two bidders, let's think of n bidders bidding for a painting. So there's some number of bidders out there all bidding for the same painting. Again, we'll deal with a case of private value. So each person wakes up, they have their own value for how much they think that they really want the painting. Now let's be a little more elaborate. So we'll allow the values to go anywhere between 0 and 100. So the type spaces are 0 to 100. And let's think of a uniform distribution, just to make things nice in terms of calculations. You can do this for more elaborate calculations, but a uniform will keep our calculus fairly simple. So they've got an even chance of being anywhere between 0 and 100. That's a given bidder's value. They're independently distributed, so what I think the painting is worth tells me nothing about what other people are thinking it's worth. So for each person, I think that they're just going to get a random draw uniformly between 0 and 100 of what the painting's worth. First price auction, we all submit bids in an envelope to the seller. The seller opens up all the envelopes, looks for whoever submitted the highest bid. That person wins. They pay their bid, and that's the end of the auction. Okay, so action spaces now are a continuum, so we allow for people to bid anywhere between 0 and 100. Their utility from what the actions are as a function of the types. Here, the only thing determining my value is what I wake up thinking it's worth. What other people think it's worth does not affect my payoff. Their actions will, but their actual types won't. So we'll call this private values. So we can ignore the theta minus I in this case. So we can write the utility as a function of what the bids are and what my value is. I don't care what other people's values were, just whether they outbid me or not. So if I have the highest bid, then I end up getting a value of theta I minus whatever I bid. If somebody else outbids me, then I get nothing. I don't win the auction. I just go home empty-handed. I don't pay anything. I don't get the painting. If I tie with some number of bidders, then we'll just randomly pick the winner by an even coin flip. And then so I get theta I minus AI, and just divided by the total number of tied bidders. When we're looking at this continuum case, in this particular auction, the ties aren't going to matter. So the fact that everybody is choosing bids out of 0 to 100, if they're using a nice increasing function, the chance that I tie with somebody is effectively 0. So the relevant parts of the payoff are really going to turn out to be whether I win or not. Okay, so again, we're in a fully symmetric setting. Let's look for a symmetric equilibrium. So in particular, in this case, we will look for a function where all bidders use the same function. So how I bid as a function of my type won't actually depend on my type. We'll all have some function which just maps how much we value the painting into as to how we bid in the auction. Okay. So in terms of equilibrium, what do we need for this to be a Bayesian equilibrium? We need this thing, this function, to maximize my expected utility for each type, given that others are using the same strategy, right? So what we need to do is we need, we can look, let's suppose my type is theta I. I get a certain expected utility for a bid of B. If I bid B, well, I win with the probability that everybody else bids less than B. So for all j not equal to I, how they're choosing to bid as a function of their types is less than B. So I can evaluate that probability. And then I get the value when I win of theta I minus B. And so what we need is that the expected utility for a bid B, the maximizer of this function, comes out to match what's prescribed by the bidding function, right? So we're looking for an equilibrium here. So figure out what's the bid that maximizes this, and we want this to be the same solution as the prescribed strategies for every player. Okay, so here we're going to have to make an educated guess. Let's try a linear function just to see how that's going to work, because in order for us to calculate the optimal function as a function of the bid, we have to have some way of calculating what's the probability that I'm going to win, which depends on how other people are bidding. So given the uniform distribution, let's suppose that it's a nice linear function. And in particular, let's suppose that people are just shading their values. So there's some C. In particular, we'll guess that C is going to be less than 1. So how much they bid is just some fraction of their value, right? So what's my expected utility for a bid B now? If I'm type theta I bid B. When I win, I get theta I minus B. What's the probability that I win? Well, it's the probability that everybody else bid less than my bid. My bid was B. They're all bidding C times their type. So you need C times theta J to be less than B for everybody else. That's when I win. And this is the value that I win, conditional on winning. Now here we're ignoring ties, and then at the end we'll have to just make sure that ties don't occur with any positive probability. Okay, so how do we solve this then? Well, we can now fill in what this probability is, given that we know how the types of others are distributed and how they're bidding. So what's the probability that C times theta J is less than a particular bid for everybody else? Well, that's just the probability that theta J is less than B over C for all J not equal to I, which is the probability that the highest of the theta J's is less than B over C, right? So we just need to figure out what that probability, this is going to be the probability that I win, is the probability that the max of all the other theta J's is less than B over C. Okay, so this probability that the max of the other bids is less than my bid, we've deduced that that's this expression. Well, from a uniform distribution, so we know that these theta J's are each uniformly distributed. That gives us a nice handle on exactly how to calculate this. So in particular, if we look at the probability that one of the bidders, just pick any of the other bidders, what's the probability that theta J is less than B over C? Well, with a uniform distribution, the chance that the value, it's distributed between 0 and 100, so the chance that it is less than B over C is just B over C times 100, right? So if you think about a uniform distribution, just in terms of a quick draw of the uniform distribution. So if we think of the density, so we've got the values here between 0 and 100. So what's the chance that theta J, so this is the density function of a uniform distribution, will look like this. It's at 1 over 100, goes up to 100. The chance that the value falls below B over C is just B over C over 100, this area here, B over C times 1 over 100. So we end up with this expression. So the chance that any particular value falls below that is just B over C over 100 from a uniform distribution from 0 to 100. So what's the probability that the highest value of the others is less than B over C? Well, it's just the chance that every single one is less than that, which is just the product of each one of these probabilities, given that they're independently distributed. So we just multiply all these probabilities together. We get B over C times 100 raised to the n minus 1. So now we have a nice expression for what's the probability that I win the auction when I bid B. Everybody else is bidding C times theta J. It's just B over C times 100 raised to the n minus 1 power. Okay, so we guessed a particular bidding function. We look at the expected utility now for as a function of my bid. If everybody else is bidding according to this function, then we've solved for what this probability looks like, given that we have a uniform distribution. That allows us now to get an expected utility as a function of B and the C. So if we want to maximize this with respect to b, we just take the derivative, set that equal to 0. So take the derivative of this function with respect to b. What are you going to end up with? Well, you're going to end up taking the derivative, will give you this expression. So we end up with, if you just take the derivative here of the first part, we end up with this expression, right? The minus 1 times this. Take the derivative of this, you get the theta b, and minus 1 comes down, and so forth. So we end up with a derivative here, and that's set equal to 0. So what we need to do is we can solve this for b. So now, again, this is an algebra problem, right? We want to solve this thing for b. So we're solving this equation with respect to b. What can we do? Well, there's a lot of things that simplify. The c over 100s to the n minus 1, those things are canceling out. We've got a b n minus 1 here and an n minus 2. So we'll end up with this part going away. This just becomes a minus b. You set these two things equal to each other, you end up with this, or now we end up with an equation which says that if everyone else is bidding according to c times theta j, then your best response is a bid which looks like theta I times n minus 1 over n. So what's c? It's just this factor. So indeed, we end up with an equilibrium. What does the equilibrium look like? The equilibrium looks like everybody's shading their bid. Everybody can bid according to the same function, which is just to bid n minus 1 over n times theta I. So actually, this is a very intuitive and interesting equilibrium. What does it tell us? It tells us that players are going to bid less than their value. Well, that's obvious. I don't want to bid my exact value. I'm going to end up not getting anything out of the auction. But here what I'm doing is I'm balancing off the lower I bid, I get more value when I win, but I win with a lower probability. And so I'm trading those two things off. And how much I can shade my bid depends on how competitive the auction is. And so what do we see? We see that as the number of bidders goes up, so as n increases, this function n minus 1 over n is becoming higher and higher. Eventually it tends towards 1, right? So eventually I'm going to bid very, very close to my value if I'm in an auction with a huge number of other bidders, because I know that if I bid too low, I'm going to have no chance of winning. And so I end up bidding more closer and closer to my value in order to win, and that gives me less and less value when I do win. So the more competitive the auction becomes in terms of number of players, the closer to their values they bid. So actually this is interesting in the sense that it tells us two things about the revenue in the auction. So as we increase competition, as you increase the number of bidders, two things are happening. One is the expected winning value is going to go up. So as I get more and more people out there, there's more and higher chance that somebody really loves the painting. So I get a higher and higher theta I. So I'm taking a max over a bigger and bigger set. And the fact that there's more people competing in the auction means that they're all bidding higher. So they're bidding more competitively. So we end up with a higher winning value and they're bidding more of it. So in some sense, as a seller, competition is helping me in two ways. One, it's giving me better and better draws in terms of getting somebody who really likes the painting. And secondly, it's forcing them to bid more and more competitively and bid a higher fraction of their value. And so here we get a nice analysis, a nice symmetric equilibrium, which gives us some good insights into how the first price auction works. So with this in hand, now we can start looking at other auctions, do some comparisons. So Bayesian equilibrium is going to be a powerful tool for understanding economic behavior and a whole series of other behaviors when there's incomplete information.